Section 1.7, Polarization. Learning Objectives. By the end of this section, you will be able to 1. Explain the change in intensity as polarized light passes through a polarizing filter. 2. Calculate the effect of polarization by reflection in Brewster's angle. 3. Describe the effect of polarization by scattering. 4. Explain the use of polarizing materials in devices such as LCDs. Polarizing sunglasses are familiar to most of us. They have a special ability to cut the glare of light reflected from water or glass, figure 1.32. They have this ability because of a wave characteristic of light called polarization. What is polarization? How is it produced? What are some of its uses? The answers to these questions are related to the wave character of light. Figure 1.32. These two photographs of a river show the effect of a polarizing filter in reducing glare in light reflected from the surface of water. Part B of this figure was taken with a polarizing filter and Part A was not. As a result, the reflection of clouds and sky observed in Part A is not observed in Part B. Polarizing sunglasses are particularly useful on snow and water. Credit A and Credit B. Modifications of work by Amithshas, Wikimedia Commons. 1.7.1. Malice's Law. Light is one type of electromagnetic, EM, wave. As noted in the previous chapter on electromagnetic waves. http://cnx.org/content/m58495/latest/closing parenthesis. M waves are transverse waves consisting of varying electric and magnetic fields that oscillate perpendicular to the direction of propagation. Figure 1.33. However, in general, there are no specific directions for the oscillations of the electric and magnetic fields. They vibrate in any randomly oriented plane perpendicular to the direction of propagation. Polarization is the attribute that a wave's oscillations do have a definite direction relative to the direction of propagation of the wave. This is not the same type of polarization as that discussed for the separation of charges. Waves having such a direction are said to be polarized. For an EM wave, we define the direction of polarization to be the direction parallel to the electric field. Thus, we can think of the electric field arrows as showing the direction of polarization, as in Figure 1.33. Figure 1.33. E vector. B vector. C. Direction of polarization. Figure 1.33. An EM wave, such as light, is a transverse wave. The electric E vector and magnetic B vector fields are perpendicular to the direction of propagation. The direction of polarization of the wave is the direction of the electric field. To examine this further, consider the transverse waves in the ropes shown in Figure 1.34. The oscillations in one rope are in a vertical plane and are said to be vertically polarized. Those in the other rope are in a horizontal plane and are horizontally polarized. If a vertical slit is placed on the first rope, the waves pass through. However, a vertical slit blocks the horizontally polarized waves. For EM waves, the direction of the electric field is analogous to the disturbances on the ropes. Figure 1.34. A. Direction of polarization. B. Direction of polarization. Figure 1.34. The transverse oscillations in one rope, A, are in a vertical plane, and those in the other rope, B, are in a horizontal plane. The first is said to be vertically polarized, and the other is said to be horizontally polarized. Vertical slits pass vertically polarized waves and block horizontally polarized waves. The sun and many other light sources produce waves that have the electric fields in random directions. Figure 1.35a. Such light is said to be unpolarized, because it is composed of many waves with all possible directions of polarization. Polaroid materials, which were invented by the founder of the Polaroid Corporation, Edwin Land, act as a polarizing slit for light, allowing only polarization in one direction to pass through. Polarizing filters are composed of long molecules aligned in one direction. If we think of the molecules as many slits, analogous to those for the oscillating ropes, we can understand why only light with a specific polarization can get through. The axis of a polarizing filter is the direction along which the filter passes the electric field of an EM wave. Figure 1.35. A. Random polarization. E vector, etc. Direction of ray of propagation. B. E vector. Polarizing filter. Axis. Polarization direction. E vector. Direction of ray. Figure 1.35. The slender arrow represents a ray of unpolarized light. The bold arrows represent the direction of polarization of the individual waves composing the ray. A. If the light is unpolarized, the arrows point in all directions. B. A polarizing filter has a polarization axis that acts as a slit passing through electric fields parallel to its direction. The direction of polarization of an EM wave is defined to be the direction of its electric field. Figure 1.36 shows the effect of two polarizing filters on originally unpolarized light. The first filter polarizes the light along its axis. When the axes of the first and second filters are aligned, parallel, then all of the polarized light passed by the first filter is also passed by the second filter. If the second polarizing filter is rotated, only the component of the light parallel to the second filter's axis is passed. When the axes are perpendicular, no light is passed by the second filter. Figure 1.36. A. E vector. Polarizing filter. Axis. E vector. Polarizing filter. Axis. E vector. B. E vector. Polarizing filter. Axis. E vector. Polarizing filter. Axis. E vector. C. E vector. Polarizing filter. Axis. E vector. Polarizing filter. Axis. Figure 1.36. The effect of rotating two polarizing filters, where the first polarizes the light. A. All of the polarized light is passed by the second polarizing filter, because its axis is parallel to the first. B. As the second filter is rotated, only part of the light is passed. C. When the second filter is perpendicular to the first, no light is passed. D. In this photograph, a polarizing filter is placed above two others. Its axis is perpendicular to the filter on the right, dark area, and parallel to the filter on the left, lighter area. Credit D. Modification of work by P, or 1. Only the component of the EM wave parallel to the axis of a filter is passed. Let us call the angle between the direction of polarization and the axis of a filter theta. If the electric field has an amplitude E, then the transmitted part of the wave has an amplitude E, cosine theta, figure 1.37. Since the intensity of a wave is proportional to its amplitude squared, the intensity I of the transmitted wave is related to the incident wave by I equals I0 cosine squared theta. 1.6. Where I0 is the intensity of the polarized wave before passing through the filter. This equation is known as Malice's law. Figure 1.37. E vector. Theta. E cosine theta. Polarizing filter. Axis. E cosine theta. Figure 1.37. A polarizing filter transmits only the component of the wave parallel to its axis, reducing the intensity of any light not polarized parallel to its axis. This open-source physics animation. https://0penstacks0yagi.0rg L 2 Ifyani LFE helps you visualize the electric field vectors as light encounters a polarizing filter. You can rotate the filter. Note that the angle displayed is in radians. You can also rotate the animation for 3D visualization. Example 1.7. Calculating intensity reduction by a polarizing filter. What angle is needed between the direction of polarized light and the axis of a polarizing filter to reduce its intensity by 90.0%? Strategy. When the intensity is reduced by 90.0%, it is 10.0% or 0.100 times its original value. That is, I equals 0.100 I0. Using this information, the equation, I equals I0 cosine squared theta, can be used to solve for the needed angle. Solution. Solving the equation, I equals I0 cosine squared theta, for cosine theta, and substituting with the relationship between I and I0, gives cosine theta equals square root of I over I0 equals 0.100 I0 over I0 equals 0.3162. Solving for theta yields theta equals arc cosine 0.3162 equals 71.6 degree. Significance. A fairly large angle between the direction of polarization and the filter axis is needed to reduce the intensity to 10.0% of its original value. This seems reasonable based on experimenting with polarizing films. It is interesting that at an angle of 45 degree, the intensity is reduced to 50% of its original value. Note that 71.6 degree is 18.4 degree from reducing the intensity to 0, and that at an angle of 18.4 degree, the intensity is reduced to 90.0% of its original value, giving evidence of symmetry. 1.6. Check your understanding. Although we did not specify the direction in example 1.7, let's say the polarizing filter was rotated clockwise by 71.6 degree to reduce the light intensity by 90.0%. What would be the intensity reduction if the polarizing filter were rotated counterclockwise by 71.6 degree?